Hello, my name is Dr. Howard Penrose, and I'm the Vice President of Engineering and Reliability Services for Dry-Silker Electric Motors. And in this presentation, we're going to discuss basic stator components for 2300 volt to 13,200 volt electric motors. We will discuss some particulars on stator cores, a little bit on wire and coils, also RTDs, windings, and then varnishing processes. The core lamination for an electric motor in general is usually made up of electrical steel. Now, in the older style electric motors, these were an annealed steel, and in the newer ones, they tend to be a silicone steel. The older ones would be, say, a C3, the newer ones would be a C4 or C5 rating. The older ones basically had a temperature limitation of about between 400 and 500 degrees Fahrenheit. The newer ones a little higher. These are cut thin, as in this picture here on the right, in order to reduce stray currents, or what are called eddy currents. Those are currents that circulate within a lump of steel when you pass an alternating magnet nearby, such as in processes used to melt steel. In this case, what you do is you separate those laminations and you put insulation between them in order to reduce that eddy current. This reduces the temperature of the electric motor. The material is also low hysteresis. Now, hysteresis is a loss that also generates heat, that is the restriction of a changing north to south magnetic field in an electric motor. This becomes very critical in your AC electric machines. Now, through a repair process, because what we're going to discuss is valid in both new equipment and also equipment going through repair, the new lamination you see on the left is brand new. It has the interlaminar insulation on it. It's ready to be stacked. And there'll be hundreds or thousands of these stacked on top of each other. The one on the right has passed through a burnout oven process. Now, a burnout oven is used to turn the insulation system on the windings to ash to make the coils easier to pull. In this case, it's also important to remember that you have an insulation material in between the laminations, and if you subject the laminations to a high enough temperature, that insulation will break down as well, causing a short and therefore hot spots. The maximum allowable hot spot in an electric machine under operation is 10 degrees centigrade above the average temperature of the core. The other thing that will happen in the higher temperatures, because of the rapid expansion and contraction of the material and the differences in the shape of the material, such as in the tooth area and the back iron area, which is below or on the outside of these pictures, you will also have the steel that makes up the core. As these all expand and contract at different rates, you'll get a waviness. This increases what are called the stray load losses and fringing, meaning that the magnetic fields do not go in the direction they're supposed to. They'll flare outwards a little bit, which is also a loss. The result is hot spots, increased operating temperature, energy cost increases, and reduced reliability if this should happen to the core. Now, the stator core itself has many of these layered laminations, and seeing as we're talking about the larger machines, once you get up to a certain dimension of core, it requires special cooling. So what you do is you would create air spaces in between smaller stacks of lamination, and that air space is there to allow cooling air to come up through the windings and through the core from the rotor in order to keep the machine cooler. Now, you see in this picture here, there's a bubble straight down the center of the picture. That's actually some copper left over from a failed winding. Now, when you do have a machine and you're getting ready to repair it, or even prior to manufacturing per the NEMA MG1 2010 or per the IEEE 1068-2009, you want to look for hot spots in that core. Now, this has been a process that's been in place for close to 100 years. And what you do is you wrap coils around the machine, and you do two types of things for hot spots. First, or for core loss. First is you will excite the insulation system to 105% of its saturation level, and you'll look for hot spots which should be no more than 10 degrees centigrade above the ambient. This is per IEEE standard 432. Then you want to increase, you want to also monitor the core and take certain measurements in order to figure out the watts per pound loss. That's the actual losses generated through the operation of the machine. It's a combination of both your hysteresis and your eddy current losses. Now with the wire is very important. On your larger machines, some still use enamel, which you'll see on the next slide. But once you get above 30 volts per turn in a machine, you'll want to use at least single Dacron glass over enamel or single glass over enamel. This increases the volts per mil stress capability of the interturn winding, reducing the chance for a direct turn-to-turn short. On motors that see a higher volt per mil or that have room for the extra insulation, you may use a double Dacron glass over enamel or double glass over enamel. This also allows the wires to move because they will grow and shrink depending on the temperature of the core. Now in this case, these pictures are partially unwrapped coils during an inspection process, and the double Dacron over glass is the white material immediately around the wires. Now for your much larger machines, say your 6,000 volt and 13.2 kV machines, basically anything over about 6,000 volts, you may use also a mica turn tape. That would be mica insulation wrapped around the individual turns of the motor in order to withstand the voltage stresses there as well. This particular picture is of straight enamel wire. Now one of the problems that we're noticing these days is that through the either manufacturing process of the enamel wire, they may be over or under cured, causing some problems with the turn insulation, meaning that the insulation may flake up from the conductor, or they may not be able to abrade properly. Additionally, if the turns are relatively sharp or too much tension is put onto the wire, you may end up also causing problems such as what you'll see on the left-hand image in the upper center and along the edges of this wire. And you'll notice the edges are also rounded a little bit. You'll notice the cracks. Those are actual cracks through the enamel straight to copper. This is of course of a concern, and one of the reasons why most repair shops, including in the IEEE 1068 2009 motor repair standard, you'll note that they recommend at least single glass over enamel. Now, we will discuss global VPI in a little bit, but as well as in resin-rich or B-stage insulation systems, what you want in these size machines is to make sure you have no voids between conductors. The voids between conductors have slightly different capacitance to the rest of the insulation, and at some point in lower voltage machines, you'll begin to get something called partial discharge. But more importantly, when you get above 6 kV or 6,000 volts, you'll get a much higher rate of partial discharge. These are little lightning storms. The result, of course, is that the lightning storms generate ozone. The ozone eats away the insulation system and eventually will turn into a short. It's important to remember that 85% of winding failures are due to turn-to-turn or coil-to-coil shorts and not insulation to ground. That represents less than 15% of your actual winding faults. Now you'll notice that in this case you've got a dark space in between. This is a section of a coil after it's been vacuum pressure impregnated, it's been cut, and then this visual inspection is being done with a microscope at 40 time at 40 time magnification. The upper right, you'll see the layers of the ground wall insulation, which in your larger machines are wrapped around the coils instead of using slot insulation systems in the windings itself. These are often layered in terms of what are called half lap, where each turn you go around and then you come back around again, and half the width of the coil is over half of the other tape that's being coiled. The result, of course, is that for each turn you end up with, in effect, 2 layers. And then you'll have as many half laps as possible, both to allow the machine to fit in the slot, and for that you want about 9 to 11 thousandths clearance on a side so that the coils can slip in properly, and then the global VPI will glue it into place. This is a green coil, also alternately called a dry coil. This is being set up for as a sample coil to go into a VPI tank along with the stator in order to prove that the stator has received a full slot fill. And the whitish material underneath it's actually an insulation material that's going to go around the edges to simulate a slot. Some people also use a sandwich layer of steel to perform the same thing. These are called resin-rich or partially cured coils. Usually these will come from the coil manufacturer with the ends not fully cured, but the end slot portion of the coil cured. Now these are normally used in above 6,000 volt coils, but can also be used in lower voltage coils. These are above 6,000 kV or 6,000 volts. Primarily you can tell that because of that black tape. That is a semiconductive tape to reduce corona discharge to ground and partial discharge. That is a semiconductive tape that has to extend roughly ½ an inch beyond either end of the stator core slot area. They can be green for global VPI'd systems, so it's not unusual to also have a global VPI on the sides machine. As the coil is being manufactured, these are sample pictures of a series of coils through the process. The first thing you'll notice on the upper right hand side is kind of a small loop. That is how the coils initially turned. Then it goes into a machine called a spreader. The spreader takes a specific measurements and then bends it so that it's shaped to slip into the slot. Then you may also have filler or felt tapes either within the coil or in the slots themselves. The coil is then taped, and it may have a mica tape as well as polyester or mica back tape around it. This is a winding RTD. Now, winding RTDs are like little antennae, but they have a certain resistance based upon temperature, and these go down in the slots between the lower half and the upper half of the coil. Often what you'll find is that you will have 2 of these per phase normally, and they'll normally be near a connection point. Now this is the stator windings being laid into the slot. This is actually the machine that was shown that we were doing the core loss test. There will be in some machines what's called a top stick. The top sticks will, in all machines of this size, will be top sticks, but you'll have 2 types. One will be just a standard top stick made out of a hard material that's insulated, or it may be what's called a magnetic top stick, which has magnetic properties. That is to reduce permeance and to simulate a closed top to that slot. Now you'll also have in-betweens. The in-betweens are there to reduce the abrasion between the coils. You actually want to make sure that the coils are separated by specific distances depending on the voltage rating of the machine, the voltage rating of the coil, in order to prevent abrasion and shorting. You'll also have around the head of the coil, both sides, you'll have what's called a surge rope. The surge rope is often a felt material that's wrapped around the end turns, then tied to the end turns, as shown in the right-hand side. You can see some of the rope hanging down as this stator is being wound. The surge ropes, during the VPI process, fill with varnish and become hardened when they cure, reducing coil movement, coil end movement during operation. You can also have a solid bracing, which might be an insulated steel or insulated wood material or other fiber. They're insulated and the windings are tied directly to them, such as in the upper left and the right. Also, between the coils, to prevent the coils from rocking back and forth or moving back and forth, you will put spacers between the coils to reduce that movement. This is often referred to as felt. The felt is placed between the coils, and there may be more than one set between the coils, between each set of end turns, depending on the bracing requirements of the machine. In some cases, when there's a large width, fiber shims may be used along with the felt in order to make up space. You also have to connect and braze or weld the top connections of each of the coils in order to make your overall connection. And then those connections are made out to other connections and so on. The connections are soldered or welded and then wrapped. Completed B-stage winding on the right it can be performed, and the one on the left is a set of green coils meant for a global VPI. Now, the global VPI process is quite interesting. This is a fairly common tank in this picture. The stator is warmed up to a specific temp. Often it's right around 204 degrees. It's then placed in the tank and a vacuum is drawn. When the vacuum is drawn, all of the little air bubbles in the insulation system expand outwards, with some of the air escaping and the rest generating what amounts to a sponge. This will be roughly 60 minutes to 2 hours, depending on the size of the machine. Once you get to that point, you then flood varnish from the rear tank into the forward tank. Now, in a lot of cases, you will perform a continuous monitoring capacitance test of the stator. That is, measurement of between the conductors and ground using capacitance. Now, what you'll notice when you have it in dry and in a vacuum is you have a relatively low capacitance value. When you flood the tank, the value begins to come up. Now, you'll maintain a vacuum for roughly 5 to 10 minutes, and then you will then go from a vacuum of near vacuum to a pressure of roughly 90 psi on the machine for the soaking process. Now, this causes all of those expanded bubbles to rapidly shrink, drawing the varnish insulation through the tapes and into the center of the coil. The capacitance value will then begin to increase. Now, there are tables that are provided with the insulation systems that give you a rough idea of how long. However, it's much better to watch, and then when the capacitance reading plateaus and levels off, you either take that amount of time, or if it's shorter than the time recommended for that size machine, you would go with the longer time in either case. In this case, on the left here, the front tank is your pressure vessel, which is normally dry except during the soaking cycle, and the rear tank is the storage, in this case a storage and cooling system for the varnish in order to maintain it. Following the VPI process, you will then take the stator and put it in an oven, as shown in the far background in this picture, and you will process the varnish in order to cure it or cause it to harden. This process for the particular system we're showing requires the stator core temperature to hit approximately 300 degrees Fahrenheit for a period of time that's based upon the size of the machine. Now this is what a globally VPI'd stator looks like. You get varnish over all of the surfaces, which can also help protect the winding. So for instance, if you are in an abrasive or acidic atmosphere, then you would want a global VPI in particular in order to protect all the steel surfaces. Now this picture is of a standard shop core loss tester. This is used to identify the hot spots again, but it's a programmed system. It's usually meant for your smaller machines. Other tests that are normally performed as the stator is manufactured is your PD surge or your surge test, your straight resistance, your insulation resistance, your high pot test. Now you may also during the manufacturing phase do what are called capacitive tip-up tests or power factor tests of the windings. Those tell you the operating condition of the insulation system. There are other tests that can be performed, including offline partial discharge testing for detecting whether or not you're going to have problems in the finished machine. In all machines, your stator is not, but your rotor needs to be dynamically balanced, but rotors and dynamic balancing will be covered under a different presentation. I'd like to thank you very much for spending some time with us today on discussing the basics of stators and stator insulation systems for 2300 to 13.2 kV systems. My name again is Dr. Howard Penrose. I'm with Dry-Silker Electric Motors out of Glen Ellen. We do work pretty much worldwide. We get work nationwide, and we have been performing works and developing specifications for motor and stator manufacturing and repair worldwide. You can contact us either through our website, http://www.dreisilker.com, or you can contact me directly at hpenrose@drysilker.com. Thank you very much.